This section again is about something called the Pythagorean relationship. That's the big focus of this whole chapter, actually. It's a pretty important concept to know. It's probably one of the more, if someone asks you something about high school mathematics, that's probably one of the things that they would point out, or the things that they would remember, or one of the things you learn in any high school math course anywhere in North America or anywhere in the world, probably. Again, as I said earlier, it's named after this person or a group of people called the Pythagoreans, lived about 2,500 years ago, and it has to do with right triangles. A right triangle is one that has a right angle in it. Is that a right triangle, that one that I've drawn there? Well, it's hard to tell whether that's a right angle or not. If I get it to show the angles, it's not a right angle, right? That's less than a right angle. So this is not a right triangle. So according to the Pythagoreans, this statement that they made won't work here, right? Because it says if a triangle is a right triangle, then the areas of the squares on the two shorter sides. Okay, areas of the squares on the two shorter sides, I will show you that right now. If you make a square that's attached to the shorter sides here, which are the two shorter sides in this triangle? You got three sides. You got a 5, and a 6. You got two shorter sides here, right? So if you make squares on those two sides, if I make a square on that side, the side length is 5, so the area is 25, right? The area of that square. It's tilted so you can't see the grid, but it's tilted so the grid doesn't match up with what it is. But it's a square that has an area of 25 if you could add up all those squares. If you make the square on the other side here, this one, both of those 25 each, because the side length is 5, those two areas add up to 50, right? Those two areas add up to 50. If I make a square on this side, what's the area going to be of the square on this side here? 36, right? Do the two smaller side squares add up to the bigger side square here? 25 and 25 obviously aren't 36, right? This is not a right triangle. If this were a right triangle, according to the Pythagoreans, those two squares would add up to this. I don't know if I can adjust this so it's approximately a right angle here somewhere. Let's see if I can get it close to a right angle. Maybe, almost. Well, we can do this. I can move this over here. That's a right triangle, obviously, right? And maybe let's make it a smaller right triangle here. There's a right triangle where all the sides are whole numbers too, right? The side lengths are all whole numbers. What do you notice about the areas of that? And that's the first example that you have, I think, in there. That side length is, I'll take the angles away just to make it a little more clear to see. That side length is 3, so the area of that square is 9, right? There's 9 squares in that little square. This side length is 4, so there's 16. The area of the square on that side is 16. Those two together, 9 and 16, add up to 25. That's the area of that square, right? Since it's a right triangle, the area of those two squares adds up to the area of the square on the longest side. The longest side is called, how many of you have learned the name already working through your study guide? Starts with H. The longest side, this side, the one across from the right angle, is called the hypotenuse. So if you're writing some definitions in your study guide and you've looked in the textbook and found it, that's that side, the longest side. Okay, if this is not a right triangle, like if we go like that, now do the area of the two smaller squares add up to the biggest square? The biggest square is 18. Here you got 10 and 16. That obviously doesn't add up to 18, right? If I stop at a right triangle, what's true about these two squares here? That square is 25, that square is 16. Does it add up to this? 41, it does, right? Even though this is not a very nice number there. It's not a whole number. So I'm assuming you're okay finding those definitions, right? Longest side, two shorter sides. Right triangle is one that has a right angle in it. The first example asks you, that's that first triangle we made, 3, 4, 5. 3, 4, 5 is probably the most commonly quoted or used triangle that works for this, right? Where they're all whole numbers. You can't just make if you just make a random right triangle, chances are the lengths aren't whole numbers. Make sure you can go through and answer these questions. It talks about writing an addition statement between the areas of the three squares. Maybe first of all you should write the area of the three squares. These didn't, I don't know how well they photocopied on your thing, but the area of the three squares, there's the area of the three squares. Make sure you can write an addition statement as in 9 plus 16 adds up to 25, right? Or you could write it as, or another good way to write it would be 3 squared plus 4 squared equals 5 squared. I would write that. Those are both addition statements. And then it says describe using words and symbols the relationship between the side lengths. You can write it in words and say exactly what the Pythagorean relationship says. Or, if you square the lengths of the two smaller sides and add them together, you get the square of the length of the longer side. Or something like that in your own words. Okay? And then definitely read how it's worded in the textbook. It's worded a little differently than I wrote it for you on that web page. And use your own words to describe what that relationship is and make sure you understand it, okay? If you understand this as you work forward from here, you will be absolutely fine with everything we do. This is a more difficult question, the second example. Well, I'm going to assume you're going to go and finish the show for the first example. Draw a little picture. It doesn't have to be to scale or anything like that because 15 centimeters is pretty big. When you're trying to do the second question, this is asking you, is this a right triangle? You should be able to use the Pythagorean relationship to show whether it's a right triangle or not. Because remember what it says here, Pythagorean relationship. If it's a right triangle, then the areas of the two smaller squares adds up to the area of the bigger square. So if you want to know if something's a right triangle, you can use that concept. Don't just go, oh, here's 5, here's 7, here's 9. Yeah, it looks sort of like a right triangle. That's not what we're doing, okay? I wouldn't do this one by drawing it because remember I asked you a triangle, I think, that looked something like, I don't know how big it was. It was something like this, I think. When I said, is that a right triangle, you said, yeah, maybe. Yes, no. Can you tell just by looking at it and drawing it? Can you tell just by that, by saying whether it's a right triangle or not? You can't, right? Even if you use a protractor, you might not be able to tell exactly. If you use the Pythagorean relationship, that's a way to prove that it's a right triangle or not. I can prove to you that was not a right triangle because those two don't add up to that. So in that last example, that's what they're looking for. They're looking for you to be able to use the area of the squares to decide. And then explain your answer. Have a look in the textbook. See what they do. Okay? Anyways, and then that's it for those two examples. And if you can get through that and you understand and everything, you can fill out the key ideas and then get going on the assignment. You should be good for this section. Okay? Make sure you're asking if you're not sure of anything. All right? Can you get going?